Thank you. So now we'll discuss one-sided confidence interval. So till now we discussed two-sided confidence interval. That's mean we calculated the lower bound and we also calculated the upper bound. Okay, so for some specific problems, sometimes we might not be needed to know the lower bound and the upper bound both. So we might be interested only about the lower bound or only about the upper bound. So in this case, you have to use the formula for one-sided confidence interval. And this formula is a little different from the two-sided confidence interval because alpha is the significance level, or this is also called the probability of type on error. Okay, so what does it mean? That's mean when we'll be constructing the confidence interval, we can make the type of error, maximum type of error, and which is alpha. So for one-sided confidence interval, for two-sided confidence interval, we use z alpha over 2 for the critical value. But for one-sided confidence interval, because why do we use z alpha over 2? Because when we construct the confidence interval, so this is our confidence interval. So this area, so this is our lower bound. So that's mean lower confidence limit, and this is upper confidence limit. So this confidence interval doesn't cover the whole area of the distribution. So we have some area here outside the confidence level. So this is, we consider 50% on the left and 50% area on the right. So that's why we divide the alpha. This is alpha over 2 and this area is alpha over 2. But if we construct just a single confidence interval, so for example, if we consider only the lower confidence interval, so that's mean we have only this area and this area is alpha. So that's why we consider z alpha. And for the upper confidence limit, if we have just one confidence interval, one bound, then this is the area outside the confidence bound, and this area is alpha. So this value is z alpha. This is actually negative z alpha. Yeah. Okay, so you can see that in the formula, the critical value is not z alpha over 2, now it is z alpha. So the when you will be calculating the upper bound for two-sided, it was x bar minus z alpha over 2 times sigma over square root of n. And this one was x bar plus z alpha over 2 sigma over square root of n. And for one-sided, for the upper, if we just want to calculate the upper confidence bound, then it will be just mu less than x bar plus. For upper confidence interval, it will be x bar plus, and the critical value will be just z alpha, not z alpha over 2, sigma over square root of n. And for the lower confidence limit, lower bound, it will be mu greater than, that's mean mu cannot be less than this value. So mu greater than, we are 95% or 90% confident that mu is greater than this value, x bar minus z alpha times sigma over n. The only difference is for two-sided we have z alpha over 2, and for one-sided we have that z alpha. Okay, and it's also same for the proportion. So if you want to calculate the one-sided confidence limit, it will use the similar type of formula. So one of the difference is here it will be the z alpha, and the other things will be same. And for lower bound, it is p hat minus z alpha square root of p hat times 1 minus p hat over n. So now we'll go over an example. So an article provided that the following summary data, one shear strength for a sample of 3/8 inches anchor bolts. N is equals to 78, X bar is equal 4, the sample mean is 4.25, and the sample size is 78. The sample standard deviation, so this is the sample standard deviation, which is 1.330. Okay, so now the question is, can we use normal distribution in this case for the sampling distribution? Can we consider X bar as normal distribution in this case? Anyone? Yes. Yeah, we can use X bar, we can consider X bar as normal because the sample size, even though for to construct the confidence interval, we can assume that X bar is normal because N is large, right? Even though sigma is not given, we are considering S is equals to 1.30. So that's mean we have the sample standard deviation, not sigma. So if we do not have sigma, the distribution shouldn't be normal distribution. And I'll tell you the reason why we cannot consider normal distribution. But we can use the approximation. We can use the central limit theorem. If n is large enough, then we can consider the distribution of X bar as normal distribution, and so that we can use Z alpha. So, and in the later section, we'll discuss about sampling distribution when n is not large. Okay. So we'll calculate the lower confidence bound. So we have to calculate the lower confidence bound, and the confidence level is 90%. So our confidence level is 90%. So alpha will be 1 minus 0.90. So it will be 0.10. So you have to find Z alpha because this is one-sided confidence interval. So that means 0.10, and which is, you can use the calculator or you can use the table to get the value of Z alpha, which is 1.282. Okay, sigma is not known. We do not know sigma. We can use the estimate of sigma. And the estimate of sigma is S. The value of S is 1.30. So that's why we are using 1.30 for sigma, though we do not know the sigma. So the lower bound is mu greater than X bar minus Z alpha times sigma over square root of N. So X bar is 4.25 minus Z alpha is 0.10. So Z 0.10, and sigma is estimated by S, which is 1.30 divided by square root of N. So mu greater than 4.25 minus this, we plugged in this value here, times this one, and the lower limit of the confidence bound is 4.061. If you construct two-sided confidence interval, you won't get this lower limit for the two-sided confidence interval. Okay, so we'll go over another example, and this is one-sided confidence interval for P parameter P. So here we are given the sample size N is equals to 143. So 143 individuals who received ceramic hips between 2003 and 2005. So that's mean this individual is our sample size, 143. So we have to calculate the lower confidence bound at 95% confidence level. So our confidence level is 95%. So alpha is 1 minus 0.95. So this is 0.05. So this is our significance level. So we have to construct the lower confidence limit for P. So that's why we have to find P greater than P hat minus Z alpha times square root of P hat times 1 minus P hat divided by N. So we have to actually find the value of this part. So we have to find the value of this part. Okay, so here sample size is 143, X is equal 10. X is the number of success. So if we read the question, the technology underlying hip replacements has changed as these operations have become more popular. Starting in 2003, highly durable ceramic hips were marketed. So unfortunately, for too many patients, the increased durability has been uh, counterbalanced by an increased incidence of squeaking. So here our interest is how many of hip replacements is quaking. So 10 of the hips developed is quaking out of 143. So our interest is, we'll consider if a hip replacement has developed squeaking, that will be considered as success. So we have 143 individuals. That's mean the sample size n is 143, and 10 of them developed squeaking. So that's mean here the number of success is 10. So how can we calculate the proportion? The p hat is not given directly, but you can calculate p hat here. P hat is equals to number of success divided by sample size. So here the sample size is 143 and X is the number of success, which is 10. So the P hat is 10 over 143, which is 0.0699. So Z alpha, that means Z 0.05 is 1.645. Now we have to find the lower bound for P, which is P hat minus Z alpha times square root of P hat times 1 minus P hat over N. So plug in the value of P hat, which is this one, then value of Z alpha 1.645, and square root of P hat is this one, 0.0699 times 1 minus 0.0699 divided by sample size N is equal to 143. So if you simplify this one, the proportion will be 0.03482. So the lower bound is 0.03482. Do you have any question? So in this section, we have learned about the confidence interval, how to construct two-sided confidence interval for mean and also for the proportion, and one-sided confidence interval for mean and one-sided confidence interval for proportion. Okay, so if you do not
Can you
have,
take it back to 7.1? I need to snap 7.1. I missed 7.1. This is snap.
sorry,
Could you take it back to the slide of 7.1? I want us to snap the page. I
uh,
missed that.
7.1.
Yeah,
So
I want to snap the page. Like I wasn't in class when you started. I wanted to snap the lecture.
yeah,
Okay,
so
yeah, thanks.
here this is the 7.1.
Okay, so what is this topic about basically?
Oh, this is just a little discussion. So you do not need, if you want, you can read, you will get the idea of the confidence interval and inferential statistics.
Oh, okay. Wait. Let me snap that. Let me snap that. The first. No, not this. Could you go?
Do you have any other question?
Oh no. But there was a page you were on. But never mind. I just snapped the page, but I guess.
Mhm. Okay. So we already covered this one, right? Yeah.
Okay.
Yeah, we already covered this one. Yeah. So in 7.3, we'll discuss about intervals based on a normal population distribution. So here intervals based on normal population distribution. That's been we know the population distribution. Population distribution is normal distribution. Here sigma is unknown and the sample size is small. Okay. So in the previous section, our assumption was also normal distribution, and sigma was for the first one, sigma was known, and x was normal distribution, mu sigma square, and sigma was known. That means sigma was given. So we constructed the confidence interval for mu. So now we have the distribution of our population. That's the distribution of x, which is also normal distribution with mean mu variance sigma square. And here the sigma is unknown and the sample size is small. So we already discussed if sigma is unknown and the sample size is large, we can still use the normal distribution to construct the confidence interval. But what will happen if the sigma is unknown and the sample size is small? So in that case, we cannot use normal distribution assumption. So in that case, we have to use some other distribution, which is called student's t distribution or t distribution. The properties of the t distribution are similar. So it is also bell-shaped and symmetric, but the difference is it has thicker tail than the normal distribution, because um, that's mean it has more values on the tails for t distribution. So we'll construct the confidence interval for one population mean. That's mean we have just one population, and we'll construct the confidence interval for mean and for small samples. So if sigma is unknown and the sample size is small, you cannot use normal distribution. Usually in real life, we do not use normal distribution for constructing the confidence interval, because most of the case sigma is unknown. Okay, so our test statistics. So how do we standardize X bar? If X bar is normal distribution with mean mu and variance sigma square, then we standardize X bar as Z is equals to X bar minus mu sigma over a square root of n. So that's how we standardize X bar. So this is normal distribution with mean 0 and variance 1 if sigma is known. If sigma known, then the distribution of X bar was Z will be normal distribution with mean 0 and variance 1, because this is the standard normal distribution. But if sigma is unknown, if sigma is unknown, then Z is no more normal distribution. So this is not a normal distribution. So now we have to find the distribution of, since this is random variable, we have to find the distribution of X bar minus mu sigma over square root of n. If sigma is unknown, we can use the estimated value of sigma. So what is the estimate of sigma? Estimate of sigma is S, right? So instead of sigma, we can use S. So X bar minus mu divided by S over square root of n. So this is the So we used S as sigma here, right? So what is S? S is the sample standard deviation, right? We know that S squared is equals to 1 over n minus 1 summation of I is equals to 1 to n xi minus x bar squared, right? So this is the sample variance. So S will be a square root of S squared. So that's mean a square root of this one is our S, right? Okay. So now what is the distribution of, this is random, S is random variable, right? Because S is function of X, because S is equal 1 over n minus 1 summation of xi minus x bar. So in the formula of S square, we have different x's, right? All the x's here. So that's mean this is also a random variable. So in this case, the only random variable was x bar. It was only random. The other values were fixed. Mu was fixed, sigma was fixed, n was fixed. Now we have two random variables. X bar is random and S is also random. Since X bar is random, it has some distribution. And since S is also random, it also has some distribution. So this is actually the distribution ratio. This is the ratio of two distributions. And for normal distribution, we know that it's just one distribution. It is not a ratio of two distribution. But this value is a ratio of two distributions because we have two random. So this one is random and S is also random. So that's mean X bar has some distribution and S also has some distribution. So that's mean the whole thing is a ratio of two distributions. Now, the ratio of two distributions also follows some special kind of distribution and will drive the distribution. Okay, so we can rewrite this one as x bar minus mu sigma over a square root of n. So in the numerator, we didn't have sigma over a square root of n. So we just incorporated this one in the numerator. Similarly, we will divide the denominator by sigma over a square root of n. Okay, so now what will happen? We can cancel out sigma, right? And okay, so we do not need to. Okay, so now what is the distribution of this one? This is already, we know this is the distribution of, this distribution is normal distribution with mean 0 and standard deviation 1, right? So the distribution of the numerator is normal 0, 1. Now we have to find the distribution of the denominator, this one. So how can we find the distribution of this one? So in the denominator, we have S over a square root of n and sigma over a square root of n. So we can just write this one as S over sigma. So we can just write this one as, so this is S over sigma. But we know that 1 n minus 1 S square over sigma square is, I'm not going to drive this one, but I'm giving you this information. The distribution of this one is chi-square distribution with n minus 1 degrees of freedom. So this is called chi squared distribution with n minus 1 degrees of, I'm sorry, I should write degrees of freedom. So degrees of, I'm writing here, FREE. So This is called chi-square distribution with n minus 1 degrees of freedom. So now if we want to write this one as this, then it will be actually, so we can write, so if now we have in the denominator we had s over sigma, right? In the denominator we had this one. Okay, but we know that n minus 1 times s square over sigma square is chi-square distribution with n minus 1 degrees of freedom. Okay, so what will happen if we take the square root of this? So if we take the square root of this, then it will be this one, then it will be a square root of n minus 1 times s over sigma, right? But in the denominator, we have just s over sigma. But here we have one extra term. So what we can do, we can just multiply with this one. And divide by square root of n minus 1, right? We have s over sigma. So now this one can be written as square root of n minus 1 times s over sigma and 1 over square root of n minus 1, right? Now from here we can see that, so what is this part? This part is the square root of chi-square distribution. So that's mean we are taking the square root of chi-square distribution. So this one can be written as square root of chi-square n minus 1, and in the denominator we have n minus 1. So what we are doing here actually, we are dividing the chi-square distribution by its degrees of freedom, and we are taking the square root of this, right? Is it clear? So basically what we are doing here, we are dividing the chi-square distribution by its degrees of freedom. This is the chi-square distribution in minus 1, and degrees of freedom is in minus 1. So what we are doing here, we are dividing the chi-square distribution by its degrees of freedom, and then we are taking the square root of this. That's the denominator. That's s over sigma. So finally, what can we say here? So x bar minus mu s over square root of n. This is actually, the numerator was normal distribution and denominator is a square root of chi squared distribution divided by degrees of freedom. So we can write when s is, so when sigma is unknown, when we use s instead of sigma, this ratio is actually the ratio of standard normal distribution, and the denominator is a square root of chi-square distribution divided by degrees of freedom. And this distribution has a name which is called t distribution, and the degrees of freedom will be the degrees of freedom of the denominator. So since the degrees of freedom was n minus 1, so it is df means degrees of freedom, or you can write t n minus 1, because from the previous page you can see the degrees of freedom was n minus 1. So this is the degrees of freedom n minus 1. So we can say that actually this is t distribution with n minus 1 degrees of freedom. So this is also called student's t distribution. And there is an interesting story about the name of this t distribution, student's t distribution. Okay. Now you can see why we are using t alpha over t n minus 1 when we are using S instead of sigma and the sample size is small. If the sample size is large, then you can still use Z distribution. You can still use Z alpha over 2 n minus 1. But since here n is not large, n is small, you have to use T alpha over 2 and n minus 1 is the degrees of freedom. Okay, so similar to the Z distribution, you can find the value of this one T alpha over 2 n minus 1 from the T table. So the formula is similar formula, X bar plus minus the critical value. Here we have T alpha over 2 n minus 1. And in the previous case, it was Z alpha over 2. And the n minus 1 here is the degrees of freedom. So for normal distribution, we do not need degrees of freedom. But for T distribution, we need degrees of freedom. That's why we have n minus 1. Okay, so you can use the either you can use the table or you can use the calculator to get the value of T alpha over 2 n minus 1. Okay, so now the question is for X bar or for mu, you can use two different formula. You can use Z interval or you can use T interval. So which interval we should use? Actually, it depends on the sample size, is depend on the value of sigma. If the population standard deviation sigma is known, then you always use Z interval. But in reality, sigma is most of the time sigma is unknown. So if know the sample standard deviation, then use Z interval if you know the sample standard deviation, not the population, not sigma. Then if n is large, then use Z interval. If n is small, then use T interval. So another way to state the decision criteria. So Z interval if sigma known or n is greater than equal 40, and T interval if sigma is unknown and n is less than 40. So if sigma is known or n is greater than equal 40, you can use Z interval. But if sigma is unknown and n is less than 40, then you should use T interval. Do you have any question? Yeah, I know that the derivation of the T distribution is really difficult because I think most of you do not have that much idea about the distribution, about different distributions like T distributions, normal distribution, and F distribution. So it is quite difficult to understand the derivation of the T distribution. But I did the derivation so that you can just get the sense that why we are using two different distribution. So what is the reason? So I just wanted to give you the reason. So you do not really need to understand the derivation of the T distribution right now. Okay. Do you have any question? Okay, so now we'll go over an example. A sample of 14 joint specimens of a particular type gave a sample mean proportional limit stress is 8.48 MPa. So that's mean the mean sample mean X bar is 8.48 and sample standard deviation S is 0.79. So the confidence interval is 95%. So alpha is 0.05. And sample size n is equals to 14. So which confidence interval we should use in this case? Can anyone tell me which confidence interval we should use in this case? T distribution, yes. So why T distribution? The first thing is whenever you see S, be careful. First determine whether you will use Z or T. If you have S, not sigma, then look at the sample size. If the sample size is small, use T distribution. If the sample size is large, use Z distribution. Yeah. But if sigma is given, then whatever is the sample size, it doesn't matter. Always use Z distribution. Okay. So here we'll use T distribution to construct the confidence interval. So the formula is X bar plus minus T alpha over 2 n minus 1 is over square root of n. So this is the formula. So now plug in the value of X bar, which is 8.48, and this is T alpha over 2. Actually, this is not Z, it should be T 0.05 over 2, so 0.025. And the degrees of freedom, you should also write the degrees of freedom. So whenever you will be using T distribution, always write the degrees of freedom, n minus 1. So this is 0.025 and n is 14. So 14 minus 1 is 13. So the degrees of freedom is sample size minus 1. So sample size is 14. So n minus 1 is 13. So now look at the T table. So the area is 0.025, and the row, in the row you will be given the degrees of freedom. So you have to use these two values to find the value from the table, from the T table. Okay, so and the critical value is better to use the calculator to find the T value. So the T value is 2.160. You'll so plug in this number here, and S is 0.79 from here, and sample size is 14. So 0.79 over square root of 14. So if you simplify this one, then the lower limit is 8.024 and upper limit is 8.936. So this is the confidence interval. And the interpretation is, we are 90% confident. Do not write the probability, because if you write the probability, then there is chance that you might do mistake. So that's why it's always better to write, we are 90% confident that the true proportion limit, not the true proportion, sorry, true mean. So yeah, they write true mean. The true mean limit, proportional limit stress is between this number and this number. So it's always better to write, we are confident. Do not write the probability that the mean will be between these two numbers. So you can use calculator. So to find the confidence interval by using calculator, if you have TI series, then you can press stats button, then scroll over to tests and choose T interval. T interval is number 8. And for input highlights, you have to highlight the stats to give the input and enter the rest of the requested information. So you will be requested the sample size, you will be requested to insert the alpha value, you will be requested to determine the side, whether you are constructing the T interval for one-sided or two-sided. Okay. So here is the instruction to use calculator to find the confidence interval. Okay, so similar to the large sample, we can also construct the one-sided confidence interval for the small sample. So the one-sided confidence interval is mu less than X bar plus, for the upper bound, T alpha, instead of alpha over 2, it is alpha, and n minus 1 times S over square root of n. So this is, only difference is here T alpha, not T alpha over 2. And for lower bound, it will be mu greater than X bar minus T alpha comma n minus 1 times S over square root of n. So now we'll go over an example. So a sample of 26 offshore oil workers took part in a simulated escape exercise. So the sample size n is equals to 26, and the mean time is 370.69 seconds. So this is the X bar, and the standard deviation, that's mean the sample standard deviation, is So how do we know that this is the sample standard deviation? Because this is the standard deviation of a sample, right? So that's why this is sample standard deviation. So we are given S, we are given the sample size N. So here N is 26, X bar is 370.69, S is the 24.36. So alpha is 0.05. So now we have to construct the upper confidence bound for mu. And this is, since n is small here, the sample size is only 26 and sigma is unknown. So we'll use t distribution. So x bar plus t alpha n minus 1 times s over a square root of n.
Okay, why is it T distribution again?
Okay, so when we use z distribution, we use z distribution if, okay, so use z if sigma known or n is large.
Uh,
So in this case, sigma is unknown and n is not large. N is also small. N is 26 only. Large means usually for confidence interval, usually comes n greater than equal 40. But this is not always fixed. It depends on the sampling distribution. But for now, you will consider if n is greater than equal 40, you will consider n as large. If n is less than 40, you will consider n as a small. Okay. So you will use z distribution if sigma is known or n is large. You will use t distribution if sigma is unknown and n is a small. So that's mean if s is given and n is a small. Okay. Is it clear?
uh,
Here we have S, we do not have sigma, right? So now look at the sample size.
um,
Sample size is only 26, which is less than 40, right? So you will use t distribution. Yeah, very good question. Okay, then prediction intervals. Till now we constructed confidence interval. So what is the difference between prediction intervals and confidence interval? So the confidence interval usually we construct for mu, the population mean. And the prediction interval is, for example, we want it, okay. Confidence interval is for mean mu. So if you construct interval for mu, then it is called confidence interval. But if you construct interval, prediction is for individual observations. So what does it mean? That's mean confidence interval will determine um, where the mean mu lies between. That's mean we find two numbers and we are confident, we are some specific percent of confident that mu will be between these two numbers. And prediction interval means you collected a sample. Now, if you collect another observation in future, so what will be the two values? The future value will lie between. These two values are called this range is called the prediction interval. So that's been prediction interval for a future observation, for a single observation. And confidence interval is for mean. So now, do you know the difference between confidence interval and prediction interval? Is
Yes, I
it clear
think so.
now?
Yes.
Okay. So now, since confidence interval and prediction intervals are different, the formula is also different. So what is the formula for confidence interval? The formula for confidence interval is for mean is x bar minus, if we use z, then it will be z alpha over 2 sigma over square root of n mu less than x bar plus g alpha over 2 sigma over square root of n.
Give me a sec. Let me write that down.
Yeah, so this is the confidence interval. This is
Well, why is it so long?
confidence interval. You already have this formula on the lecture note, so you do not need to write down really
Okay,
write down.
but what of for the T and Z
Oh,
distribution?
so t and z will depend on the value of sigma and the sample size. Yeah,
Like so like for this thing for Z that sigma and for T that sigma is not meant to be used. How do you now work that out? Because T sigma is not meant to be used, and the sigma in this formula at all.
yeah. So I've already mentioned that we use z when sigma is known.
Mm.
Yeah. So
And T when sigma is unknown.
yeah,
And
sigma is
sigma is
unknown
known
and
here.
n is small. Sigma is unknown and n is small. Yeah. So,
Yeah, so can you use T for this formula?
sorry.
Can you use T for this formula since sigma is known?
Yeah, I just gave yeah. So it will depend. It will depend on on the problem, like whose problem you are solving. Yeah, I'm just giving the general formula to give you the idea of the difference between two intervals, like the prediction interval and the confidence interval. So yeah,
About like
you can also say if the n is a small, then you can also yeah say alpha over 2 n minus 1 is over square root of n mu and x bar plus t over alpha over 2 n minus 1 is over square root of n. Yeah. So if you use t distribution, if s is given and n is a small, yeah, then you can use this one. Yeah.
okay.
Okay, so now if you look at the formula for the confidence interval for, sorry, prediction interval, then you can see the difference is here. The other things are same. This is x bar plus minus t alpha over 2 n minus 1 times s. The difference is this is a square root of 1 plus 1 over n. So this is the difference times a square root of 1 plus 1 over n. So in the previous formula, we had just a square root of 1 over n. So what was the formula for confidence interval? So for confidence interval, it was t alpha over 2 n minus 1 s times a square root of 1 over n, right? So if you separate n from s, then it will be, so here, if you separate n from s, then it will be actually s times, we can write this one as s times 1 over a square root of n, right? Yeah. So only difference is we have one extra one added, right? With 1 over n. So we added an extra one. So actually this one came from, so why do we have this one here? Why did we add this one with 1 over n? So we added this one because this is the prediction interval, and the prediction interval actually comes from, I'm just giving you a little bit idea of the prediction interval, but I'm not going to drive it because it will take time. So for confidence interval, we use actually x bar minus mu sigma over square root of n. we use this statistics, right? Now our statistic is this one for confidence interval. But for prediction interval, so why do we use this one? Because we construct the confidence interval for mean, and mean is the population mean, which is mu. But for prediction interval, this is confidence interval. And for prediction interval for PI, this is for individual observation. So that's mean X bar minus X sigma over. Okay, so here this is X bar minus X. And in the numerator, we had X bar minus mu divided by the standard deviation of this one. So now we have to calculate the standard deviation of this one. So what is the standard deviation of this one? The first you need to calculate the variance of X bar minus X. If you calculate this one, then finally you will find sigma square plus sigma square over n. And for this one, the variance of X bar minus mu, what is the variance of X bar minus mu? Can anyone tell me what is the variance of X bar? Okay, so what is the variance of X bar? Do you remember? The variance of X bar? Anyone? So what is the distribution of X bar? The sampling distribution of X bar. Normal distribution with mean mu, and variance is, do you remember from the previous class? Anyone? Sigma square over n, right? Yeah, sigma square. Yeah, sigma square is the variance of X, but variance of X bar is sigma square over n. Yeah. So that's why we divided here. And if you find the standard deviation of X bar, then it is sigma over square root of n. That's why we divided this one by sigma over square root of n. Now, the variance of X bar minus X is sigma square plus sigma square over n. Now, if we factor out sigma square, then it will be 1 plus 1 over n. And this one we can write. Now, if we take the square root of this, so variance of X bar minus X, we found sigma square 1 plus 1 over n. And variance of X bar, we found sigma square times 1 over n. Now you can see the difference. Here we have 1 over n, but here we have 1 plus 1 over n. So if you take the square root, then it will be sigma times 1 over square root of n. But if you take the square root of this one, then it will be sigma times square root of 1 plus 1 over n. So now you can see why do we have square root of 1 plus 1 over n in our prediction interval formula, because the variance is different, right? That's why we have a square root of 1 plus 1 over n. Okay, so the only difference is here we have 1 over a square root of n, and here we have a square root of 1 plus 1 over n. So that is the only difference between the prediction interval and confidence interval. Okay, so to construct the confidence interval, you have to.
What is the difference? What is the difference between prediction and confidence?
Sorry.
What was the difference between prediction and confidence again?
Yeah, that's what we discussed, like why the prediction interval and confidence interval is different, right? Because the confidence interval is for mu, mean, and the prediction interval is for X, for an individual observation, for a single observation. So that's why we have the variance is different from the variance of a single observation is different from the variance of the statistics for mean. Yeah, that's why we have different formula for prediction interval and confidence interval.
So I
Okay.
didn't get that.
Uh-huh.
You said we had different formulas because so
Yeah. So the difference you can see here. Here we have 1 over n plus 1. But in the previous one, we didn't have, we had 1 over n, square root of n, but we didn't have this one, right? In the previous one, we didn't have plus 1. But here we have plus 1. So that's the difference. Okay, so now the question is, which interval is wider? Okay, so I can write the both the interval for you. So now you have to determine which interval is wider. Okay, so give me a second. So the confidence interval is x bar plus minus, or you can write x bar plus minus. Okay, and prediction interval is x bar I'm using z for both case. It could be also t. Yeah. So which interval is wider? First compare square root of 1 over n and square root of 1 plus 1 over n. Yes, prediction interval. Yeah, you are right. Prediction interval is wider because the margin of error for the prediction interval is larger than the margin of error for confidence interval. You can compare these two values. So square root of 1 over n versus square root of 1 plus 1 over n. Which one is larger between these two numbers? This one is larger, right? Because we have here plus 1 with 1 over n, but here we do not have plus 1. So that's mean this one is larger. So that's mean since this part is larger and we are multiplying with this one, so this part is larger than this part, right? So that's mean the margin of error is larger than the margin of for prediction interval is larger than the margin of error for confidence interval. So that's why the prediction interval is always wider than the confidence interval. And that also makes sense because if you want to give a range for the value of a single observation, it should be wider than the range for the value of mean. Yeah. Okay, so now and you can also construct one-sided prediction bound, the upper prediction bound and the lower prediction bound. So in this case, instead of alpha over 2, you will have just alpha. That's the difference. Okay, so we'll go over an example here. A sample size of 26 offshore oil workers. So sample size is the same example. It is 26 and the standard deviation is 24.36. And this is the sample mean. We have to find the 95% prediction interval for the escape time of a single additional work. So if we consider an additional worker, so what will be the interval for the escape time of that worker? Not the interval for the mean escape time. That's why this is prediction interval. So you'll use the formula for the prediction interval, plug in all the numbers, and if you simplify, then the prediction interval will be 319.552 to 421.828. Now you can see the confidence interval for this problem was that we constructed only the upper bound, so we can compare the upper bound. So here the upper bound is, for the prediction interval, the upper bound is 413.089.
what did you say?
And the upper bound for mu was 378. So that's mean the upper bound for prediction interval is way larger than the upper bound for confidence interval, right? So that's when the interval became wider. Yeah. Do you have any question? Okay, so if you do not have any question, I'll give you 3 minutes for the attendance. And after that, we'll start the next section.
Give me a sec.
Uh-huh. Sure.